Okay, so we are recording and we are continuing now section 5.2. We're talking about characteristic equations, and we have an important example that actually relates to dynamical systems. And that's actually what we're looking at here is example 5 in the textbook. So let me give you a moment to copy this example down, and then we'll discuss its solution. Okay, so remember Markov chains. Okay, Markov chains, we had a migration matrix. Okay, we had a migration matrix, and I can never get the point. Hold on here. Yeah, and when we multiplied the migration matrix by the population distribution initially, we got the population distribution x1. Okay, and then I'm sorry. The population distribution after 1 year was represented by the vector x1, and we found that by taking the initial population distribution x sub 0, that vector of probabilities or percentages, and then multiplying it by the migration matrix. Now, after 2 years, if we want to know the population distribution between the city and the suburbs, we took m times x1, and that got us x sub 2, which is the population distribution between the city and the suburbs after 2 years. Okay, so uh, certainly it's not a big jump to say, okay, well, if we multiply a vector x sub k by a matrix A, we're going to get the vector x sub k plus 1. Okay, that's not a big jump to say that, where k goes from 0, 1, 2, 3. Well, it turns out that there are dynamical systems that we can model using this iterative matrix equation. Okay, like for instance, if we wanted to find out if I want to say this the way I want to say it, if we wanted to find out if a population of the two species in a population, how they interact with each other, if we want to find out, for instance, what their eventual monthly growth rate would be, or if eventually the populations are going to thrive or go to extinction. This dynamical system matrix equation is the key to determining that, and you'll see that in section 5.6. Right now, though, we want to analyze the long-term behavior of this dynamical system. Okay, that means, of course, we want K to go to infinity, right? Okay, and we're given initially that x of 0 is 0.6 and 0.4. Now notice, what do 0.6 and 0.4 add up to? What do 0.6 and 0.4 add up to? They add up to 1. So those could be like percentages, okay, you know, I want to say it the right way. Well, those could be percentages. But let's for now just not worry about that. So, okay, this comes from section 5.2, this example. Chapter 5 deals with eigenvalues and eigenvectors. So, of course, eigenvalues and eigenvectors are going to get involved here. So, okay, let's go ahead and look at how we do this. So, first of all, we can use MATLAB to help us get eigenvalues and eigenvectors. Now, for your section 5.1 homework, I don't want you to use MATLAB to help you get eigenvectors and eigenvalues. I want you to work the problems out by hand, because that then shows me you understand the concepts, and you know your next exam, I would be looking for that, right? But for, like if you have a matrix A, like here, okay, and this goes with example, let's see, this is section 5.2, example 5. The matrix A is this matrix 0. Hold on, let me do it right here. Okay, so, well, no, we wrote down the matrix A here, right? Here it is. And when you have decimals like this is not like it's not exactly a easy matrix to work with, for instance, in doing row operations and so forth, or finding, solving the characteristic equation, determinant of A minus lambda I equals 0. So before we find eigenvectors, we have to find eigenvalues. And this is the characteristic equation, but it's a little bit hard to work with because you have these decimals. Okay, now the example 5 in the book, they actually work it out by hand, and that's okay. But we can, for a somewhat complicated matrix like this, where we don't have nice numbers, we can use MATLAB to help us. So MATLAB can help us get the eigenvalues and some eigenvectors. And the command that we're going to use here is this command. Okay, this command right here. So you define SYM of A, and then take the I, that'll give you of the SYM of A. Okay, and what that will generate is it will generate eigenvectors and eigenvalues that are stored in the eigenvector matrix V and eigenvalue matrix D. Now, SIM of A, hold that thought, one moment. I'm going into MATLAB here. I'm going to open it up. And what the sim of A does, it ensures that you're going to get fractional answers in your eigenvectors, or I'm going to be careful how I phrase this. You want to have nice, clean values for your entries of your eigenvectors and for your eigenvalues. Using the sim of A command will ensure that. Okay, so let's just go into MATLAB here. Hold on here, one moment. And so bring up your MATLAB, sim stands for, it creates symbolic variables, expressions, functions, and matrices. That's what the sim command does. Okay, so let me just show you how I'm getting this. Let's see. One moment here. Can everybody see the MATLAB okay on the screen? Okay, good. Thank you, Cameron. Okay, so let me see. Let me take this one off. Okay, so thank you, everybody. So if I click on the little FX thing there and type the word sim, it brings up sim, and it has like information on that command. Okay, you have to. I mean, like I click on it and it brings it up, but it's going to basically make the numbers, if they can look nice, they're gonna be in a nice form. Okay, a nice form. Okay, so what I'm going to do is I'm going to go ahead and type this matrix A. Okay, and let me just see now, since I got to have it kind of in front of me here to do this. One moment. Okay, one moment here. No, a half and 3/2 is just fine for matrix. There's nothing wrong with those numbers, but a good question. You'll see here. You'll see. Okay, so here is my matrix. Here's my matrix. And actually, that matrix is the same matrix as we did in section 4.9 with the Markov chain, the migration matrix example. Okay. So what I'm going to do is type in this command. Now, one moment here. Let me just go. So I'm going back and forth here. I heard there are a few chats here. All right, very good, Mikhail, very good. Okay, very good. So type this, and you see I get fractional answers. Okay, so like if we were to do it, let me just try something here, class. Let me just try something. If we were to take out the sim of A, if we were to just do I of A, see that? See what we get? We get decimal approximations. We don't want that. MyMathLab doesn't want that either. Like when you type in answers and stuff, it's not going to accept those decimal approximations. It wants exact answers. So this is why This is why, I'll do CLC to clear that. This is why we need to use IG of CIMAVE. Okay, does that help clarify that? Now, look at what we get. We get a matrix of CIMAVE. All right, hang on. I don't know. Let me just see. Hold on. I never even thought about this. Yeah, okay, I guess it's turning the matrix A into, it's writing those decimals as fractions. Okay, so I never even thought about it, but all right. Mikhail, so you're good. All right, so let me go back here. All right, so here is the matrix V and the matrix D. Now don't worry about the presentation. The matrix V, it looks like there's two row vectors, right? And the matrix D, it looks like there's two row vectors, but ignore that. Look vertically. So the eigenvalues come from the matrix D. The matrix D has along the diagonal values of 23/25, which in the book, of course, they have it as 0.92. And then you have the eigenvalue of 1. The eigenvectors in the matrix V of this matrix A, if you look vertically, -1, 1 is the first eigenvector, and then 3/5 and 1 is the second eigenvector. Okay, so those are your eigenvalues and corresponding eigenvectors. So the eigenvalue of 23/25 goes with the eigenvector -1, 1. The eigenvalue of 1 goes with the eigenvector, the second eigenvector, -3/5, 1. Are there any questions so far? Give me a thumbs up if you're okay with this. Okay, Marcelo's good, Cameron's good. Mikhail's good. The matrix V contains your eigenvectors. The matrix D contains your eigenvalues. And that's just how they're presented using this command. Very good, Jacob, you're good. All right, Mikhail, very good. You know, Mikhail, why are they formatted like that? I'm honestly not sure. And I suppose maybe they can be formatted differently given some kind of command, but basically I have seen this used a lot. So, and we want to keep our code simple. So, okay, all right, now let's go back to the example. Okay, so now here we are. Here is the first eigenvalue and the first eigenvector that we saw. And here is the second eigenvalue and corresponding eigenvector that we saw from MATLAB. Now remember, the eigenvector, the second eigenvector, 3/5, 1, any multiple of an eigenvector is also an eigenvector. So the eigenvector with entries 3 and 5 would be an eigenvector for the eigenvalue equal to 1 as well. We generally like to use nice eigenvectors because it just makes things easier for us. Now we're interested in this I want to say everything the right way. In this dynamical system, we're interested in the long-term behavior. Okay, so in other words, again, the dynamical system here is x of k plus 1, x at time k plus 1 equals the matrix A times x of k. And we want to know, as k goes to infinity, what happens? Well, it turns out that we can actually use these eigenvalues and eigenvectors to help us answer this question here. So first thing we can recognize is if we were to take any vector in R squared, okay, we can write, well, these eigenvectors live in R squared, right? And there are two of them. So the set of eigenvectors v1, v2 has to be a basis for R squared. And this means that the initial vector x sub 0, remember, what was x sub 0? In the problem, the vector x sub 0 was equal to 0.6 and 0.4. But this initial vector, or initial stage vector, x sub 0, can be written as a linear combination of those two eigenvectors because the eigenvectors form a basis for R squared. I mean, they do, right? Two linearly independent vectors in R squared form a basis for R squared. So what we're going to do is we're actually going to write x sub 0 in terms of this linear combination of the eigenvectors of that matrix A. So that means we have to find what C1 and C2 are. Well, this is a vector equation, and a vector equation will give us a system of equations. So we can go and solve that. Right? And that's what we're going to do. Are there any questions so far? Okay. So here's the system. Here's the system that we want to solve. And this gives us this augmented matrix. And we could do row operations and show that C1 equals 0.225 and C2 equals 0.125. Okay, we could do that, no problem. Okay. And incidentally, that initial vector of point, hold on here. Yeah, the initial vector of 0.60 and 0.40. Hold on, let me get this a little bit nicer. The initial vector of 0.60 and 0.40 does correspond to that example we did with the migration matrix, because we started off with initial distribution where 60% of people live in the city and 40% of people live in the suburbs. So in the end, when we determine the long-term behavior of this dynamical system, which is in this case the migration matrix example we did, we should end up with the same result that we got. Effectively, if you recall that migration matrix example, we learned that eventually 37.5% of the population will be living in the city and 67.5% of the population will be living in the suburbs. In other words, 3/8 of the population will live in the city eventually, and 5/8 of the population will eventually live in the suburbs. Okay, but let's not worry about that now. So, okay, I mean, what we want to do here is we want to determine what is the limit as k goes to infinity of x sub k. That's what we want to find out. Now, it turns out that, of course, well, x1 equals a times x sub 0. Okay, but x sub 0 is equal to this linear combination of the eigenvectors, where C1 is 0.225 and C2 is 0.125. Look at what we can do, though. We can write this expression like this, and then C1 and C2 are those constants. They can be factored out of the matrix products. But then you have A times V1. A times V1 will equal lambda 1 times V1. Why is that? Why is A1 times V1 equal to lambda 1 times V1? Why would that be? Why is A times V1 equal to lambda 1 times V1? Why would that be? We're replacing A times V1 by lambda 1 times V1. Why can we do that? And incidentally, we're replacing A times V2 with lambda 2 times V2. Why can we do that? But why? Why can we just do that? Why is A times V1 equals lambda 1 times V1? Why is A times V2 equal to lambda 2 times V2? Why, though? What gives us the right to the ability to take A times V1 and replace it with lambda 1 times V1? Why can we do this? Come on, think. What are V1 and V2? Those vectors. What are those vectors? Okay, Mikhail, and why is that? What are V1 and V2? What kind of vectors are those? Good, they're eigenvectors of the matrix A. What are lambda 1 and lambda 2? Those are eigenvalues of the matrix A. That's right. So we can do this. We can substitute for A times V1 lambda 1 times V1. We can substitute for A times V2 lambda 2 times V2. And so the vector x1, which is going to actually be the population distribution of that migration matrix after 1 year, that can be written as C1 times 0.92 times V1 plus C2 times 1 times V2. Now, what about x2? What about x2? How can we express x2, which is the population distribution after 2 years? That equals A times x1. And for x1, we can substitute in this expression here. C1 times lambda 1 V1 plus C2 times lambda 2 V2. Because X1, let me see here. I want to say this the way I want to say it. Yeah, all we're doing is we're taking this here, which is what the vector x1 equals, and we're substituting it down here. And then we play the same game. We rewrite the expression this way. We factor out well, we can factor out the constants or the scalars, which are C1 and lambda 1. We can factor those scalars out. And now we end up getting C1 times lambda 1 squared times eigenvector V1 plus C2 times 1 squared times eigenvector V2. Why are they squared? Okay. Yeah, take a look there. Take a look. This is x sub 2. That's okay, Mikhail. Good. We're taking our time here. We're taking our time. All right, let me just write something here. So x sub 1 equals this linear combination of the eigenvectors. X sub 2 equals this linear combination of the eigenvectors. What do you think x sub k? What would x sub k equal? C1 times something V1 plus C2 times something times eigenvector V2. What's going to go here and here? Almost right, Mikhail. Almost right. 0.92 to what power? These were first powers here. Right. See that? So now you have an expression. That's okay. I want to be careful here how I write this. One moment. Right. One moment. Yeah. Now we have a formula. That's right. That's right. Now we have a formula. So you see, you can see there's a pattern. There's a pattern here. There's a pattern. So x sub k equals C1 times 0.92 to the kth power times eigenvector V1 plus C2 times 1 to the k times eigenvector V2. In other words, in general, what we can say is this. I mean, we can make a general statement here. Well, I mean, here's what we have. Here's what we have. We have that x sub k is equal, well, it's going to equal C1 times 0.92 to the kth power times eigenvector V1 plus C2 times 1 to the kth power times eigenvector V2. 0.92 is lambda 1, 1 is lambda 2. And this is true for k equals 0, 1, 2, dot, 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 dot. Is everybody okay with that? The stage vector k. So this would be the population distribution, for instance, after k years. It can be expressed in terms of the eigenvectors of the migration matrix A, in this case. But this can be generalized to other situations also. That's right, Mikhail. So it's really an absolutely beautiful result here. Now, again, what are we looking to do? We're looking in C1 and C2, we know what those values are. We know C1 is 0.225 and C2 is 0.125, right? We know that because we found those. So what we want to do is find the limit as k goes to infinity of the stage vector x sub k. In other words, that's going to tell us what the long-term behavior of the dynamical system is. So if we go back now to here, in general then, this is what we have. Now what I'm doing is, and let me just see here, hold on, I want to check one thing before I go in there. One moment. Go back to that whiteboard. Yeah, so, okay, yeah, and those are the eigenvectors, V1, V2. So let me go back here. Almost done here. So now, this is what we know. And we'll put in those eigenvectors. Now, what does this term here, 0.9 to the kth power, what does this approach as k goes to 0? It goes to infinity. You have an eigenvalue less than 1 being raised to the kth power. What is that going to approach That approaches 0. That's right. I mean, do it in decimals. Take 0.92 and raise it to a big number, and you're going to get a very small number. It'll probably put it in scientific notation, but you're going to get a very small number. So what happens is the first term here, as k goes to infinity, then the first term drops out. Or we can say that goes to the vector 0, 0 as k goes to infinity, because that factor goes to 0. Now 0.1 to the kth power for any as k goes to infinity, I mean, well, that just equals 1. So as k goes to infinity, the limiting behavior of the dynamical system is 0.375, 0.625. And that's equivalent to 37.5. Eventually, the population distribution of the cities will become about 37.5%. In other words, eventually 37.5% of the population will live in the city, and 62.5% of the population will live in the suburbs. So this example is another way of finding the steady state vector, okay, for your for the migration matrix, okay, steady state vector. Let me see, there was a comment here. Well, yeah, in this case, because one of the eigenvalues was 1 to the kth power was equal to 1. But of course, that doesn't have to happen if you deal with different applications. So we're going to learn about, for instance, looking at species. Do the species thrive over time? Do they grow? Do they go to extinction? Do they remain stable? We can ask a lot of questions, and all of these questions can be answered based on this concept that the stage vectors can be written in terms of the eigenvectors of a matrix A. How many think this is like one of the most beautiful ideas you've learned in math? This idea. I mean, how many think this is like very cool? Yeah, I agree, Jacob. It's pretty cool. Pretty cool. Okay, Mikhail. Well, I said one of the most. One of the most. But I understand, Cameron, and I hope my these copious notes I'm giving you that really give a lot of detail help you. Okay, Cameron. All right. I mean, this is cooler than Candy Crush, right? Right? You all like Candy Crush, I think. So, okay. Cameron knows what I'm talking about. Well, Jacob, sines and cosines are pretty cool, but wait, you watch and see. When we get to section 5.6, this is who knows? You might have you might think it's up there, but top 10%, I'll take that. That sounds good. Are there any questions on this before I stop the recording? I mean, this is section 5.2. We've covered it pretty well now. Are there any questions? Okay, I will stop the recording then. Very good.